So as I already told you that we are defining X as we are setting the X as orthogonal complements of two vectors. So that is I can have a row space and the null space. So here the row space, how do you get the row space? From the column space itself you can get the row space. So we can say that the row vectors are going into the column space because you'll be taking the transpose of A and then you'll be calculating row space. So it goes to the column space and the null space goes also goes null space goes to x and ax equals to 0 and that is axn equals to 0. So you have the null space goes to 0 and row space goes to column space. So the you can define x in terms of the figure. The same thing can be explained with this figure that you have a row space, you have a row space xr and which is of the dimension, what will be the dimension of the row space, and it is equal to r, and the dimension of column space will be n, and here the next null space the is dimension is n minus r, and the row space goes to, when you write in terms of matrix, row space goes to the column space and the null space goes to the 0 point, that is null space goes to x and equals to 0, and whole this is we are splitting x in terms of xr and xn, and when you have x equals to xr xn, that automatically goes to the solution goes to the column space itself. So you know the dimensions of left null space is m minus r, whereas the column space is r, and row space dimension of row space is r, and the dimension of the null space is also n minus r. So that is left as it is, and you can represent how do you find the orthogonal complements of the x by using this figure. So this is nothing but the multiplication of ax equals to b itself, but x being divided into row space and the null space, because that is what orthogonality defines orthogonality of the spaces. And we just look, we'll go through the problems. Here we have simple problems solved here. We can have, what is the first problem? We have to find out which pairs are orthogonal among the vectors v1, v2, v3 and v4. So we have one of the vector, you have to take a transpose, and the other vector you keep as it is, or you can say dot product. What will be the dot product? 1 into 4 plus 2 into 0 plus minus 2 into, I am talking about v1 and v2, minus 2 into 4 and plus 1 into 0. So this leads to what? Here 4 and here 0, and here it is minus 8. So we lead to it as minus 4 because minus 8 plus 4. So these are not orthogonal. Now you can write in terms of v1 here and v2, v2, that is v transpose. So it comes in a row wise, and v2 as it is, and just multiply the matrix multiplication, you will be getting it as minus 4. So it is not equal to 0, so they are not orthogonal. So you can write like this or using a dot product. So next you can similarly find out the other combinations to check whether v1 and v2 are not orthogonal, right? So it's automatically understood that v2 is also not orthogonal to v1. It's not necessarily to check v2 transpose and v1 again. So once you have checked v1 and v2, it's over. You can check for v1, v3, you can check for v1, v4, and then you can check for v2 and v4, all the possible combinations of the vectors you can check. And then if the values, wherever you get the product and the dot product equals to 0, then those are orthogonal, otherwise they are not orthogonal. Another problem here, find the length and the inner product of x. Inner product of x is nothing but just again the dot product. So that will tell you whether they are orthogonal or not. And finding the length from the Pythagoras theorem, right angle triangle. So you can have the vector length equals to square root of 1 square plus 4 square plus 0 square plus 2 square. whatever the value that is here, we are getting it as 21, square root of 21. So we will be getting it as the length of x. And similarly for y also we can do square root of 2 square minus 2 square, 1 square, 3 square, that is leading us to square root of 18. So these are the lengths, and then the inner product is 1 into 2, that is 2, and plus 4 into minus 2, that becomes 8, and 0 in plus 1, 0 into 1, that becomes 0, and 3 into 2, that becomes 6, and this is equals to 0. You can say the vectors are orthogonal to each other. Give an example in R square of linearly independent vectors that are not orthogonal. We have to give an example such that they are of linearly independent vectors. The vector should be linearly independent, and also they are not orthogonal. Also give an example of orthogonal vectors that are not independent. So independent vectors should not be orthogonal, and the orthogonal vectors should not be independent. That's why you have to write and give an example. So here I have given one example. You can try for the other combinations if you can. That is, if x is 1, 0 and y is 1, 1, you can see then they are clearly independent. X is not depending on y, or y is not depending on x. 1, 0. You cannot say y has 1 times of x, or x has 1 times. They are not dependent. They are independent. So x and y are independent, and just check whether they are orthogonal or not. You can see 1 into 1 gives you 1, and the other 1 plus 0. So it is equal to 1. So that is, they are not orthogonal, because if you get 0, then they are orthogonal. This is one example. Another you can give is similarly you can give orthogonal vectors 0, 0, 1, 0 we have taken. So here they are here 0, 0 when I take. So it is x is 0 times of 1, 0. So x comma 0, 0, this automatically becomes what? Whenever you take an example of x 0 comma 0, this is always a dependent vector, because any vectors, if I multiply it with 0, it becomes 0, 0. So that vector becomes dependent, not independent, and hence the transpose of that you are getting it as 0. So they are orthogonal, but they are not independent. They are dependent. Next example, if I look into the other example. So here also the same type of problem is asked. You have R square and linearly independent vectors that are not orthogonal. That already we have seen. So here an different